Hello. In this video lecture, we will be covering Chapter 12, Mechanical Waves and Sound. It should be, I hope, an interesting chapter. We begin with the study of mechanical waves, and then later on we will cover the subject of sound, which is an application to what we will study in mechanical waves. When we say a mechanical wave, we mean a wave that you can see with your own eyes in general. For example, when you are looking at ocean waves, that would be an example of a mechanical wave. Or the wave that you would see on a wheat field. For example, if you're in the countryside in Iowa or something, you would see a wave, a mechanical wave on a wheat field as the wind blows on it. Another one is when you drop a stone in a still pool of water. You will see circular wave propagating in the radial direction away from where the stone was dropped. That would be also an example of a mechanical wave. I think there is a picture here on the second page. Something like that. There we go. See, when you drop a stone or something like that, you will see those circular wave moving away from where the stone was dropped from the center. And that's also an example of a mechanical wave. Or also when you have a rope like this one and you would move it up and down, that's also a mechanical wave. So there are two types of waves. One is called transversal waves, and one is called longitudinal wave. There it is, transverse wave and longitudinal wave. I'm going to talk about them briefly, but please take the time to read the chapter for more details. Okay, so the shape of a typical wave, and it can be described by a sine function or a cosine function. I think we talked about that in the previous chapter. Because mechanical waves, or waves in general, they possess periodic motion, and as you know, sinusoidal functions such as sine and cosine are periodic functions. So it would be ideal to take the sine or cosine to describe this periodic motion, and that's why we use sine and cosine. So when we represent it graphically, we represent it as a wave or a sine function or a cosine function. For our book, I believe we use sine rather than cosine. It doesn't really matter, they're both equivalent. Anyway, so a typical wave would look something like that, which is like a sine function. Here is your, say, your y-axis, and this is the x-axis like that. And then it will look something like this. I can do a better job with chalk. There we go, something like that. And if we assume this is the, let's say the x-axis, and this is the y-axis, more details on that later. So the height of the wave, if you remember from previous chapter, we call it the amplitude, right? So this is the amplitude right here. And we remember the period. We said that the time it takes to complete one cycle, and the frequency is the number of cycles per second. You can go back to the previous video and review all that. There is also another interesting variable, which is called the wavelength. The wavelength is the length of one cycle, okay? So you can start, for example, from here. Let me use my mouse so you can see it. From here, at the origin right there, all the way until the end of the cycle, which is right here. So we can go from here all the way until here, and that would be the length, what we call the wavelength, the length of the cycle. Or you can do it from peak to peak. For example, from this peak right here, from this peak right here to this peak right here, that would be another way. It's exactly the same thing, no difference. That's also lambda. Okay, lambda for wavelength, that is, or from trough to trough, which is from here to here. Again, doesn't really matter how you measure it. Okay, so we define lambda, the Greek letter lambda, to be the wavelength, and it's one word. Okay, and then we have A, the amplitude. And then we have, as the wave is moving, let's say you are moving a rope up and down, okay? So the wave would be, let's assume it's moving in this direction. This is the velocity of the wave, you know, the velocity or the speed of propagation. So here we have the v is the speed of propagation. Just like that, okay? And like I said, there are two types of wave, transverse wave and longitudinal wave. Again, take the time to read it in the book, but I'm going to talk to you very briefly about it. The wave that you're looking at, such as the ocean wave or the wave on a rope or the string guitar or whatever, these are all transverse wave, not longitudinal wave. How do I recognize the transverse wave? Here is how. Okay, look at the wave here. Here is the amplitude, right? This is the amplitude. And look at the velocity vector. If you think, what is the relationship between the amplitude and the velocity? You notice that the amplitude is perpendicular. See, it goes up and down like that, the wave as it moves. It goes up and down like that as the wave moves, let's say, to the right, okay? So as you can see here, for a transverse wave, is that the amplitude is perpendicular to the velocity. Okay, this is called a transverse wave. Transverse wave. Okay, so basically that's one way to recognize it. Okay, then you get the other kind of wave. It's called the longitudinal wave. Longitudinal wave. And the longitudinal wave is actually the velocity is parallel to the amplitude. Maybe I should go to the amplitude is parallel to velocity. Is parallel to the velocity. Let me make a drawing of it, show you how it looks. Let's say you have a slinky. I'm sure you are familiar with a slinky. Let's say that you have a slinky and then you extend it, you know, some distance. So, and then you fix both ends. So here is one end right here. Here is the other end. And then you get the slinky stretched, okay? You stretch it, you know, some distance. Doesn't have to be really tall, but some distance like that. And then you fix both ends like that, okay? So the spring here, the slinky, is at rest, okay? Imagine that you would grab the slinky right somewhere in the middle. So let's say here, okay? It doesn't matter, it doesn't have to be in the middle. Let's say somewhere here. And you would grab it and then pull it this way. So let's say I grab it here with my hand and I pull it this way, okay? And I pull it from, say, up to a distance x here, okay? So some displacement x. And then once it reaches this point right here, I let go, okay? I'll let go. So what will happen to the slinky? What will happen to it, it will start oscillating as a wave, but not like the transversal wave, like an ocean wave or something. It will actually oscillate like that. Okay, it will oscillate left and right like that. As a matter of fact, it will have a little, it will look something like, let me draw it again, just give you a better picture. So it will be oscillating left and right in such a way that you will see certain points here where there will be a compression and then an expansion. So there will be a compression area here, a compression region, and then an expansion region, and then another compression region, and then another expansion, and so on, like that. Okay? So this area would be called compression region. And this one right here is an expansion region. Now, and so on, okay? So notice here that the amplitude of the wave, whether in the expansion region or in the compression region, is in this direction. Here is, the amplitude will be something like that. This is the amplitude. And of course, the velocity is going to be in this direction or this direction, you know. But basically, what we are looking at is that the velocity vector, let me just put one direction. So the velocity vector and the amplitude will both be in the same direction. In other words, they are parallel with each other. And that's basically how we define the longitudinal wave. I'm trying to find a picture. Let's look at my book here of a I don't think there is a picture here of Slinky. I thought there would be one. Anyway, that's basically what it is, okay? So let's go back to where we started. So we said that the wave, and of course longitudinal, of course, has a wavelength just like you know, a transversal wave. But we will be concentrating in this chapter on this topic on transversal waves. Now there is a relationship between the velocity of the wave and the wavelength, and that is given by this famous relationship. You've probably seen it. So the relationship, the relation between the velocity and the wavelength, and this relationship is basically V equals lambda times f, such as f here is the frequency. You know what the frequency is. Again, that's from previous chapter, is the number of oscillations per second, and it's measured in hertz, the unit of it, okay? So in this case, now since the frequency is 1 over tau, tau is being the period, so we can also say that the velocity is lambda over tau. That's another relationship. Please write down those relationships as we go along. And let me give you an example. Example 12.1 from the textbook. That's on page 57. He goes on about transversal wave. Oh, that is the relationship. Let me just show it to you very quickly. Right here. So the velocity is equal to lambda f, or lambda over t, t being here the period, correct? Okay. And then this is an example right here, this diagram right here. Let me make it bigger. This is an example. It's not really a very good example of a longitudinal wave, but as you can see, this is see this dark yellow color, not yellow, blue color, and then you get this white color here and so on. So this dark blue or blue color is a compression region, and then the white one here is represented by that expansion region. Sometimes it's called rarefaction. Okay, the expansion or rarefaction region. That's an old name for it. Okay, that's basically what a longitudinal wave is. Okay, here's the example. Very simple example. He said, here we will examine the wavelength of a sound wave produced by a piano. Let's calculate the wavelength of the sound wave in air at 20 degrees Celsius if the frequency is 262 hertz. Okay, he says here the approximate frequency of the note middle C on the piano, for those of you who play piano. Assume that the speed of sound is 344 meters per second. Okay, so basically what he's saying, if you have a sound wave, and by the way, sound is a longitudinal wave, it's not transversal, he didn't mention that, but anyway, so we have here the frequency is 262 hertz, and he said the speed of sound at 20 degrees, by the way, the speed of sound changes with temperature, so they said the speed of sound is 344 meter per second. Now he's asking for what is the wavelength. Okay, very simple relation. So we know that, as you can see from here, the wavelength is right there. So lambda is equal to V over F. Lambda is equal to V over F, and you just simply plug it in. So we have 344 divided by 262, and then when we plug it in, you get 1.31 meters. So that's a very large wavelength, 1.31 meters. Okay, that's about 1 1/3 of a yard, if you will. Okay. Okay. Now, in order for waves to propagate or to move, it needs a medium. You see what I'm saying? For example, I'm talking to you right now, and let's assume that I'm talking to you live. Let's say you're in front of me, and you can hear me. And the reason because you can hear me is because there is air between us. And when I produce my sound wave from my throat, those sound waves are carried on the air molecules, and then they are transmitted to your ear, if you will. Okay. Now, however, if I would be talking with you in vacuum, let's say that we are sitting in a chamber and there is no air, and I could be screaming and making all kind of sounds, but you'll not be able to hear me because there is no medium for air, for sound to propagate. Okay. In other words, all waves need a certain medium, whether it's solid wood. You know, for example, when I knock at the table here and I hear that sound, there is sound propagating through the wood. For example, if you would put your ear right on the table, you will hear the sound through the wood because air propagates through the wood, which is a medium. So again, sound or waves need a medium to propagate. If there is no medium, sound is not going to propagate. Same thing with, say, ocean wave. Those ocean waves are not going to be moving if there was no water. You see what I'm saying? It needs a medium. So in this example, in this section, the next topic that we're talking about is that how sound, or we want to measure the speed of sound that is propagating or moving on a tight rope. And that's on, trying to find it here. Wave speeds, under the section wave speeds. Let me go back to the book. Wave speed, there we go, right here. And we have this interesting relationship right here. Let me write the formula, and then I'll talk about it. So wave speed. So the speed of wave on a rope, for example, on a tight rope, say a guitar string or something like that. And I'm just going to give you the formula. The velocity is equal to the force divided by mu, all of that under the square root. Here, the force here is basically the tension in the rope. I like to use T for tension rather than F, but so I may switch between F and T. And then here, mu, this is called linear mass density. Linear mass density. Very simple concept, really. A linear mass density basically is this. Let's say I have a string, a guitar string, and let's say the length of it, here is a guitar string, right? And let's say the length of it, suppose it's 1 meter, okay? And if I take this string and I weigh it, I put it on a scale, okay? And when I measure its weight, let's assume that its mass, or its mass rather, let's assume it is, guess the number, let's say 20 grams. Okay? So let's say 20 grams. The linear mass density, or the linear density of the string, is simply the mass of the string divided by its length. That's it. Okay? So the mass here is 20. I'm going to convert it to kilograms, so times 10 to the negative 3 kilogram, divided by the length is 1. So therefore, the linear mass density, or the linear density, is basically 0.002. Did I do it right? 1, 2, 3. No, 0.02. Sorry. 0.02. Is that right? 1, 2. Yeah. So linear mass density would be that, which is basically a kilogram per meter. Okay? So that would be the linear mass density. So simply take the mass of the string, or the rope, or the cable, or whatever it is, and divide it by its own length, and that will give you the value of mu. Okay. Let me give an example and show you how useful this formula is. Again, let me just give you another illustration of this formula. Imagine you have a guitar. Okay, so here's a guitar. And let's say that we have, let's just make it one string guitar. There we go. There we go. That's one string. And imagine that if I would pluck the string of the guitar, let's say in this location right here. So if I pluck it right there, what will happen is that a wave is going to travel all the way to the end here, and it will rebound. And of course the wave also is going to travel all the way to this end, and it's going to rebound. And what I'm interested in, let's assume this is where I plucked it right here. I am interested in what is the speed of the wave moving to the right and the speed of the wave moving. They're both going to be the same speed, I believe. Don't you think? Because it's basically the tension divided by the mu. So they're going to be the same speed, except in opposite direction. So let's say that I'm interested in the speed of that wave, and it's simply given by what is the tension in the string in Newton divided by the linear density of that string. How do I find the linear density? I take the length divided by, I take the mass divided by its length, and I will get that number. All right? Let's do an example. Example 12.2. In the book. Just this page. Oh, this right here, is it? Yes. Oh, that goes in 2 pages. Okay, let's look at this one. He says in this example we will apply equation 12.2, which is basically referring to the equation that I just showed you. He called it F sub t. All right, well, whatever. Okay, to the simple case in which tension in the rope is provided by the weight of a box. Okay, he said one end of a nylon rope is tied to a stationary support at top of a vertical mine shaft that is 80 meters deep. Okay, so we have a mine shaft 80 meters deep. The rope is stretched taut by a box of mineral samples with mass 20 kilograms suspended from the lower end. The mass of the rope is 2 kilograms. The mass of the rope, okay, he wants you to get linear density. The mass of the rope is 2 kilograms. The geologist at the bottom of the mine signals to his colleague at the top by jerking the rope sideways. What is the speed of the transverse wave? Okay, so, and there is a picture there right here. See the picture? So you get that there is the mine shaft right here. Here is the rope, and then you got this geologist right here, and at the end here there is a box filled with minerals, whatever. So the rope is tight, if you will. The height, which is the length of the rope, is 80 meters. You see what I'm saying? And the mass of the rope is, looking at my unit, 2 kilograms. And he wants to know what is the speed of the wave and the wavelength as well. Okay, he says, what is the speed of the rope? If a point on the rope is given a transverse simple harmonic motion with a frequency of 20 hertz, what is the wavelength of the wave? Okay, so let's do this problem. So it looks something like that. Let me draw the picture. So here is the height. If I can draw it better. There we go. And let's say here's the rope right here. And at the end hanging a mass right there. Okay. And the height of or the length of the rope rather is 80 meters. Just like that. Okay, so first thing I need to do, I know that the velocity is square root of f over mu. So the first thing I need to do, I need to find mu. Mu is what? Mass over length. The length is given to us right there. This is the length. So the mass, he says, is 2 kilograms. Is that right? Look at my hard copy. Yes, it is. So 2 kilograms divided by 80. Is that right? And then from there, I'll get mu is equal to 0.025 kilogram per meter. There we go. That's the linear density of the rope. Okay. The velocity. Well, before I do that, let me look at the box and the rope right here, and I'm going to draw it right there as a free body diagram. Here is the box, and here is the rope. So there is a tension T. And then there is mg. That's it. So sum of the forces in the y direction equals 0. The rope is not moving, right? So in this case, I have T minus mg equals 0. Therefore, the tension T is equal to mg, or F. We call it in the formula F. But anyway, there it is. The tension is equal to mg. Now, so I go back to this formula right here. So I know that the velocity is equal to square root of the force, which is, again, this is the tension, which is this one right here, right? So that will be mg over mu. Make sense? Just plug in your numbers. Done. So it will be square root of mg, which is, now remember, this m is not the mass of the rope. It's the mass of the box. Excuse me. The box is the one that is causing the tension. The mass of the box that is causing the tension. It's not the rope. So, so here the mass of the rope, excuse me, the mass of the box is given to us. It's equal to, I'm trying to find it, 20 kilogram. Okay, here, let's go back. I have to go back one more page. He said, there we go. He said the box of mineral sampled with mass of 20 kilogram. Got it? Okay. So here we have the mass is 20 kilograms. That's 20 times 9.8 divided by mu. I just calculated it, 0.025. And then I would calculate all of that. And then when we do it, I will end up with square root of 196 divided by 0.025, and the velocity in this case will be 88.5 meters per second. Okay, there we go. All right. Now the last part of the problem, he says, if the frequency, which is the number of cycles per second, let me read the problem again, that part. He says, at a point on the rope is given a transverse simple harmonic motion with a frequency of 20 hertz. What's the wavelength? All right. So he said the frequency is 20 hertz. What's the wavelength? Lambda, right? So we know that lambda is equal to V over F. V, I just got it, 88.5 divided by the frequency 20, and therefore lambda is equal to 4.43 meters. There we go. Okay? All right, good. Next. Section 12.4, mathematical description of a wave. Of a wave. Okay. Now this requires some heavy-duty mathematics that is not covered in our text here or in our course. There is a class of equations called partial differential equation, or the wave equation, where you have to solve that equation and then you end up with an interesting solution. So we're just going to jump to that solution basically, and that describes the wave. I want to show it to you in the book. It's on page 360. Oh, next page. And I'm going to talk about it. But basically, you don't need to worry about how he, I mean, he goes on and on about it. But what you need is this one. He said the equation of periodic wave on a string, and that's specifically for the string, okay? So we are specialized in that. And then you want to be familiar with those graphs. I'm going to go over them as well. But basically, this is the equation that we need to be familiar with, okay? T here is the period, lambda, wavelength, of course. A is the amplitude, okay? So this basically is the equation of the wave, specifically on a string. That's the one we're going to be dealing with, okay? So let me go over that. And the y here is the displacement of the wave along the y-axis, and then the x here, this is the direction of propagation of the wave. This is the displacement along the x-axis, okay? Of course, there are two parts for it. There is the spatial part, this is x, and then there is the temporal, or the time part, which is right here. So t over tau, which is time, x over lambda, that's the spatial part. Okay. So it looks something like that. Let me write it down for you. So this is called the equation of the wave. Of a wave on a string, that is. Okay? And it's equal to y equals a sine 2 pi parentheses t over tau, tau being the period, remember that, minus x over lambda. Okay? Now, you can write it this way as well. Again, this is not in your book, but I'm going to write it this way. This is my preferred version. A sine omega t minus kx. Okay? This is the more common form of the way that you'll see in different texts, for example, or if you take in maybe an MCAT exam or something, you may see it in that version. Okay, this is more popular in my opinion. Anyway, so what does that mean? Okay, so k here is called the wave number. You don't need to know what it is, but basically the wave number is nothing but this expression, 2 pi over lambda. Okay, 2 pi over lambda. Here it is. Look at it. See, it is kx, right? Here is x right here. 2 pi over lambda is k. See that? And then omega. In other words, those two symbols, omega and k, help you write the wave equation in a compact form. That's what I'm trying to say. Okay, omega is the one that we are familiar with from previous chapter and the one before that. It's the angular frequency. And if you remember from previous chapter, it's equal to 2 pi f. Remember that? 2 pi f, or 2 pi over tau, right? Because f is equal to 1 over tau. So look at that. 2 pi over tau. Remember, this is a common factor. You can multiply it out. Let me show it to you in more details. Let me just take this equation and write it down. If I would take the 2 pi here and multiply it inside, so I'm going to take the 2 pi, multiply it right there and right there. So that's going to be a sine parentheses 2 pi over tau t minus 2 pi over lambda x. And as you can see, it's right there. This is basically, this is 2 pi over lambda is k, and 2 pi over tau is omega. See that? So I can just write it as a sine omega t minus kx. Honestly, if you don't like my version, that's fine. You can just stick with the book. That's fine. It doesn't really matter. Okay. So what does that mean? More on that in a minute. Let me make a drawing of that. So here we have, again, I want to go to the drawing shown in the book. Right here, okay? So there are two versions for the, I mean, when you look at a graph of a wave, you need to pay attention to the y-axis and the x-axis. Look at that. This is y and x. So he's basically giving you information in terms of the spatial components. This is x for space. Look at this one, y and t. What does that mean? Well, remember we said that what's the definition of the wavelength? The wavelength is the length of one cycle. The length of one cycle. So say from trough to trough. So that will be the wavelength, the length of the cycle. However, the time it takes to complete one cycle is called the period. So you can't really put the period on x, you want to put it on t. So this wave is exactly the same as this wave, except this one is written, excuse me, is imposed or drawn on a t-axis, on a time axis, and that same wave is drawn on a x-axis, okay? So whenever you see a picture, always pay attention to the x-axis, excuse me, the horizontal axis, that is, and see if it is spatial or temporal. Is it x or t? If it's t, then it will give you information about the period. If it's x, it will give you information about the wavelength. You get that? All right. Okay, good. The next topic is sound intensity. This is an interesting topic. I hope you'll find it fun. and that will be on, I'm trying to find what section is it, 662. Sound intensity right here in normal modes. Okay, we're going to be concentrating mainly on I'm sorry, I'm in the wrong place. Sound intensity, what is it? Oh, I'm skipping that section. I beg your pardon. Hold on. We're going to go to, there we go. It's section 12.9, and that's page 373. Right here, sound and hearing. Okay, I'm sure you're going to find this interesting, especially for those of you who are specialized in majoring in medical field like nursing or medicine or whatever. This would be probably very interesting topic for you. Okay, so before I talk about that, I want to talk about what we call the sound intensity. Oh, it is actually next section. I'm a little bit ahead of myself. Right here, sound intensity. So I want to talk about that. So that's sections 12.9 and 12.10. Okay, I want to talk about intensity, the word intensity. It's a good word to know in physics, what we mean by that. I'm sure you know what that means in daily language. But in physics, when we say, for example, a light bulb is intense, which means it's very bright, okay? Sound is intense. The easiest way to think about it, it means it's loud, okay? So intensity here gives you a sense of loudness in terms of sound. In terms of light, it gives you a sense of brightness. You get that? Okay, this is not accurately exactly the definition, but that's one way to think about it. So when you read the word intense sound, it means it's a loud sound. Okay, now what does loudness depends on? Okay, think about this for a minute. What does loudness of sound depends on? Well, it depends on how close are you to the sound source. Make sense? I mean, for example, I could be a mile away from a siren of an ambulance, okay, and I can hear it, but it's not going to just, it's not going to hurt my hearing, for example, because I'm really far away from it. But I can hear it in the distance, okay. So it's not very intense, it's not very loud, but I can hear it. I can still hear it. So it depends on how far are you from the source. This is important. The second is that how powerful the sound source is. For example, the siren on an ambulance or a fire truck, that siren is extremely powerful. It gives off very, very powerful sound, okay? And so here you have two factors involved here for the intensity, for loudness, that is. One, how far are you from the source? That's one. And second, how powerful the sound source itself. You get that? Same thing applies for light, light, the brightness depends on what? Well, it depends on how far are you from that light source, and also how powerful the light source is in terms of how bright it is. You see what I'm saying? So that's kind of the same thing. So here, intensity depends on power of the source, and I'm going to underline the word power because I want to come back to it, and it depends on I'm writing too fast. It depends on distance. Let's say that. Okay, it depends on distance. Okay, and this intensity I, we have a symbol for it. I is equal to the power divided by the area. That's the definition, the mathematical definition, or this is how we calculate the intensity of a source. Whether it's, again, we're not covering light, But actually, if you were covering light, which is in physics 152, you will come back to exactly this formula to calculate the intensity of light, which is the brightness of light. Exactly the same formula. So maybe it's a good idea for you to learn it once and for all. Now, you may say, what in the world is area? What is that? I thought you said distance. What's the area have to do with it? Let me explain it to you. Imagine I am, let's say, as I speak with you right now. Okay, let's assume that I am in a classroom, okay, and you are in front of me and I'm talking to you. As I talk to you, you are, of course, you can hear me. Now, imagine if somebody is standing behind me. Okay, so I am facing you, but there is another person, let's say, standing behind me. Would that person still be hearing me? The answer is yes. Why? How? How is that possible? Since I am my face is directed towards you and my sound waves are directed towards you, how is it possible that the guy behind me is able to hear me? You may say, well, because there are walls in the classroom, and then the sound waves are reflecting off the wall. That's partially true, but that's not the whole truth, because we could go all the way to the desert where there is nothing there, and we would have a classroom with no walls, and that person behind me will still be able to hear me. The reason that this person is able to hear me even though he's behind me is because of the way sound or light propagates, okay? The way it propagates is this. When I say, for example, let's say here is a sound source. Let's assume this is a pole, and this is like a sound source, say a siren. And let's say that this sound source will say the word check, okay? Check, any word you want, check, okay? So how does this sound propagate? Well, it's going to propagate in a spherical waves. It's going to propagate like that. And so on. Many, many spheres. And those spheres are going outward in the radial direction, just like when you drop a stone in water. But that's a sphere. It's not a circle, a ball, if you will, that is swelling in all direction like that. So in other words, if this is a top view, here is you are, let's say that you are here, okay, and here is the person behind me, well, he will still be able to hear me because my sound source is propagating in all directions, okay? You understand that? So remember, sound and light propagate as spheres swelling. You got that? Swelling, inflating at the speed of sound. The speed of sound is roughly 350 meters per second, depending on the temperature, but let's say I assume it's around there, 350 meters per second. So those sound waves are getting bigger and bigger at that speed until they reach you. Let's say here is your ear right there, until they reach your ear, okay? Somebody's ear is here, and they will reach it, you know, at that speed and so on. You got that? Okay, so let's assume that I am able to measure the sphere that came to me right here, okay? So this is the sphere right here. If I can draw that thing right there. Okay. Well, the way intensity is defined, the one I just showed you right here, is that intensity is equal to the power of the source, you know, the power of the source right there, right? Right here, where the source is, siren or whatever, light bulb, whatever, divided by the surface area of the sphere that reaches the observer. I know that's a very long thing to put it under the denominator, but that's basically what it is. The surface area of the sphere that reaches the observer, this sphere, specifically this sphere that reached I am the observer right here, okay? Well, what is the surface area of a sphere? I'm not talking about volume. Okay, the area of a circle is pi r squared. The surface area of a sphere, we're going to call it A, is equal to 4 pi r squared. Okay, let's make it small r. It's 4 pi r squared, where r here is the radius, which is right here until it reaches the ears of the observer. That's R right here. Okay? So in other words, I'm going to write intensity in the following manner. Intensity is equal to power over 4 pi r squared. That's the idea behind this area. So we're not really measuring distance only, we're actually measuring the surface area of that sphere that has reached my ears, if you will. You got it? So this is how we define intensity. Okay, so far? Okay. Let's see if I can find an example before I move any further on that. Yeah, there is one here. Example 12.7. On page 74. Oh, it's right here. Okay, there we go. It says in this example, we will use the definition of intensity to calculate the power emitted by an array of speakers. A sound system of 2,000 seat auditorium. This is probably not important, those 2,000 seats. So a sound system for a 2,000 seat auditorium is designed to produce 1 watt per meter squared sound intensity. I forgot to mention that this is the unit of intensity. I'll come back to it in a sec. Over the surface of a hemisphere 20 meters in radius. What acoustic power, he basically looking for the power, is needed from an array of speakers at the center of the sphere? All right, let me show you what that means. .7. So basically what he's saying is that he has an auditorium. Hold on, let me just talk about the unit here. I'm sorry, let me just go back to this intensity. I want to make sure I don't want to forget it. So we said that intensity is power over area, and we know that the unit of power is watt, remember that? Divided by area, which is meters squared, so that would be the unit of intensity. Okay? All right. So he said you have the intensity, the intensity is given by 1 watt per meter squared, and the nature of the propagation of that light is a hemisphere with radius of 20 meters. Okay, so that's a hemisphere. You know what the hemisphere is, right? If I can spell it. There we go. Hemisphere looks something like a half a sphere with 1 pole. Like a cereal, bowl of cereal. That's a hemisphere. Okay, that's a hemisphere. So the sound source is right here. Basically what he's saying, remember, sound always propagates as a sphere, not a hemisphere. But he said he's basically wants you to ignore the other hemisphere, the other half. And so here is the sound source right here, and then let's assume that the observer is, let's say, here or here, anywhere on the hemisphere, and these are all R, right? These are all the same radius, or even here. So this is how the auditorium looks like, basically. So these are ears, okay, and so on. So he's asking, what is the power source here? In other words, I want to create an array of speakers in such a way that I want the intensity to reach the observers and the auditorium to be only 1 watt per meter. That's a lot of intensity, by the way. That's really loud. So what would be the power of that source? Well, we know that intensity is power over area, and the area here is what? 4 pi r squared. But because he says the hemisphere, so we're going to divide by 2. You see what I'm saying? So it is 2 pi r squared. You see what I'm saying? And so in this case, the power, I'm going to go back to this formula, is equal to IA, and this I times A, which is 2 pi r squared, and then we just plug it in. So everything is given to you, 1 times 2 pi times the radius is 20 meters squared, which is 400, and then we multiply all of that, and you will get 2,512 watts. So you want that the power of the speakers collectively to be 2,512. That's a lot of power. Okay. Okay, good. One more thing. It's kind of you may find it useful for doing problems. Imagine I have a siren, okay? This as an example, and I'm going to show you an interesting relationship. So let's say that you have a siren here. And the siren producing a sound, and a siren, of course, has a certain power. And as we said, the way sound and light propagate, they propagate in spherical waves. So here are the spherical waves around it, right? And so on. Okay. And let's assume there is an observer right here. There's the ear. Again, I draw the ear as an observer. And this observer, I'm going to call him observer 1. And she is at a distance r1 away from the source. And she will hear an intensity. She's going to measure intensity, loudness of I1. Okay, let's say she has a device that can measure loudness. And that device will tell her, well, the intensity is so and so watt per meter squared. Okay. And of course, the sound source here has a power P. Now, a person, another observer who is much, let's say, farther, okay? Here is another observer right here. We're going to call him observer 2. He is at a distance R2, okay? And he's measuring the same thing, which is the loudness or the intensity of the sound. And so he's going to measure I2. You know, you agree with me, I2 should be smaller than I1. You agree with me on that? Because he's further, so he's going to be, and of course the area of that spherical wave is going to be larger, since the denominator is going to be smaller. So anyway, so if I would measure I1, what would I1 be equal to? Well, I1 is going to be equal to power over the area, which is 4 pi R1 squared, correct? And then observer 2, he's going to measure the intensity to be I2 equals power over 4 pi R2 squared. Is that right? Okay, let me solve for power in both equations. From equation 1, the power is equal to 4 pi R1 squared I1, and the power in equation 2 is equal to 4 pi R2 squared I2. So far, so for good? Well, those two must be equal, correct? Because we're dealing with the same power, we're dealing with the same source, you see what I'm saying? So I can equate this one and this one together. So let's equate them. So in this case, we're going to have 4 pi R1 squared I1 equal to 4 pi R2 squared I2. The pi's cancel out and the 4's cancel out. And I end up with the following interesting relationship. I1 over I2 equals to R2 squared over R1 squared. It's a very interesting relationship that may come out, that come in handy later on. Okay? So keep that in mind, write it down somewhere, and we may find it useful at some point. Okay, next topic. Again, we'll come back to the intensity. This is all just an introduction to this topic, the one I'm about to show you, and that is the decibel level. I'm trying to find it in the book first. Oh, it's within, okay, under sound. Decibels. Decibels. Okay. Decibels is an equation. Okay, well, decibel is a unit that measures similar to the intensity, and it measures intensity of sound, but specifically how the human ear observe or perceive that sound. Okay, so it's specifically for the human ear, or maybe the animal ear, even for dogs and cats and so on. Okay, so it's more of an interesting unit for biologists, if you will, those who are studying animals, and especially also human beings and so on. So, and the reason we use decibels rather than watt per meter squared, because the human ear is extremely sensitive, and so we use intensities that are logarithmic. Let me explain. Here is the formula. Beta, the Greek letter beta, I'll draw it better. So it looks like a B with a long tail. Beta equals to 10 decibel, just write it down, D, small d, capital B, that's the symbol for the unit decibel, times log I over I naught. Okay, I'm going to explain all of that. Let me just write it down. Okay, this decibel is, like I said, it's a unit, and it's made out of two words, deci, which means 10, bells. Okay, and I think bells have to do with Graham Bell's, the one who studied sound. I don't know, but I think it is. But anyway, so decibels is a unit that measures intensity of sound, and it's written in logarithmic scale. I here, okay, is the intensity of sound, the one we just covered here, okay, is P over 4 pi r squared, for example, okay. I naught here is a special number. We call it the threshold of hearing. The threshold of hearing. I naught, and it's equal to 10 to the negative 12 watt per meter squared. What does that mean? When we say threshold of hearing, it means the minimum sound loudness, the minimum sound volume, the minimum sound intensity that the human ear can hear, okay? Of course, most likely with my age, I probably cannot hear that sound. If you produce a sound with 10 to the negative 12 watt per meter squared, I probably will not be able to do it. Probably a child or somebody who's a teenager or something like that will be able to hear that sound. But, so it is the minimum, the bare minimum. This is the quietest sound you can ever hear, okay? That's called the threshold of hearing. That's, you know, that's the minimum. Below that, human beings cannot hear it. Maybe the cat could hear it, or the dog, or a bird, or whatever. But the human cannot hear. So this is the minimum amount of sound that a human could hear, okay? The word threshold means that, the minimum, or at the border, okay? That's what it is. So this is a specific number that we can actually put in here. The unit of the decibel to measure the intensity of sound, again, we said that it is decibel, and this is written, that unit is written as small letter D, capital letter B, okay? This is called the decibel. Let me give you a feel for that decibel. And it's in the book. Let me go to the table. It's on page 75. Here we go. Okay. So, for example, there we go. We're going to be using, this is the intensity right here, written in watt per meter squared, and then this one, the decibel, in dB. Okay. So the threshold of hearing, like I told you, is 10 to the negative 12 right there. Okay. Imagine that you are listening to rustling leaves, or rustle of leaves, okay? So the intensity of the rustling leaves is 10 to the negative 12, or 10 decibels. See how convenient this unit is? It's kind of give you, rather than you dealing with those tiny numbers, you deal with those better numbers. So a rustle of leaves is 10 decibels. Average whisper, okay, somebody's whispering in your ear, that's about 20 decibels. Quiet radio in home, 40 decibels. Quiet automobile, let's say you have the engine on, so that's 50 decibel. Right now, as I talk to you, for example, unless you are cranking the volume really loud, it's about 65 decibel, which is like a normal conversation when you're talking to somebody in a quiet room, okay, let's say, not in a cafe with all kind of music blaring, whatever. So that's a quiet, ordinary conversation is about 65 decibel. Busy street traffic, you know, horns, streets, and all that, you get 70 decibel. elevated train, 90 decibel. I don't know what that means, but whatever it is. We don't have trains in the US most of the time. Anyway, and then you have a riveter, which is, I think it's, what is it called? A nail gun, okay? Like a drill, for example, the sound of a drill. It's 95 decibel. And then you have what is called the threshold of pain. You know, when you hear something so loud, you put your hand on your ears, because it reaches a sound where it is so loud it becomes painful. That will be 120 decibel. A rock concert, well, believe it or not, it's actually more than the threshold of pain. It's 140 decibel. Okay, so by now, I hope you have a feel for that unit now, what it is. Okay, so basically it measures the sound intensity as far as the human ear is concerned, or animal ears and so on. Okay, and this formula that I have just given you allows you to convert the intensity in watt per meter squared into decibels. Okay, that's the whole purpose of this formula. Okay, that's why I think this formula is so cool. Okay, so this formula, so given that you have the intensity in watt per meter squared, well, what is it in decibel? Well, just plug it in there, and then you'll get it. Okay, so let me show you an example of that. Let's start with example, you know what, let me, example 12.8. I want to do it, but I want to start with something a little bit easier. This is basically for my notes. It says calculate the intensity level of sound having an intensity A, B, and C. Let's start with A. I have an intensity of 1 times 10 to the negative 12 watt per meter squared. Okay, so what is the intensity level? So when we read the term intensity level, we really mean decibels. Okay, that's really what we mean. Okay, so how do we do it? Well, we know that the formula beta is equal to 10. Now, if you don't want to see, it's 10 decibel. Okay, this decibel is not necessary. If you don't want to write it down, that's okay. It doesn't affect the calculation. But basically, just a reminder that this number 10 is a decibel. But you can ignore it. So 10 log I over I naught. Okay, and all you need to do is you just plug it in. So I have here 10 times log. Now I is given to us, which is right here. Right? This is given to us. He said the intensity is 10 to the negative 12. So that's going to be 10 to the negative 12 divided by I naught. I naught is 10 to the negative 12. Remember that. I naught is always 10 to the negative 12. Okay? It's just a constant. Always. Okay? All right. So you just plug it in. And then, of course, you want to prepare your calculator. Make sure that you know how to get the log of a number. Remember, this is log to the base 10. Log of a number in your calculator, in your scientific calculator. So you have 10 here times log what? 1. What's log 1? Log 1 is 0. Okay, you can look it up in the calculator. Log 1 is 0, so that's going to be 0. So the decibel level is equal to 0, which I believe we already did that in the table. Look at that. 10 to the negative 12, 0. See that? That's a threshold of hearing. Get that? Okay. Part B. He says the intensity level is 1. I equals 1 times 10 to the negative 11 watts per meter squared. Let's do that. So again, we just go beta equals 10 times log I over I naught. So we just work it out. So 10 log 10 to the negative 11 over 10 to the negative 12. Again, you want to do some algebra before you jump to your calculator. So this is what? 10 to the negative 11. Here is how I do it. Let me do it in slowly so you can see my my steps. So 10 to the negative 11 times 10 to the positive 12, correct? When you move it up. So that becomes 10 times log 10 to the 1, which is 10. What's log 10? 1, right? I hope you memorize that. So that's 1. So the decibel level is 10 decibels. Again, we can go back. I believe I saw it on the, here we go, 10 to the negative 11, which is equivalent to 10 decibel, and that's rustle of leaves, okay? Rustling leaves, okay? All right, good. And part C, the last part, the intensity is 1 times 10 to the negative 10 watt per meter squared. Okay, let's see how we do that. So we have here beta 10 log I over I naught. So that will be 10 times log 10 to the negative 10 over 10 to the negative 12. And that gives me beta is equal to 10 times log, what is that, 100? And what is log 100? That will be 2, right? Here, let me do it without a calculator. Let me show you. Just a little review for algebra. Remember, log 10 is 1. Keep that in mind. Log 10 is 1. It's really easy. So I have here log 100. So that's log 10 squared. So that's 2 times log 10. Well, log 10 is 1, so that's 2. So log 100 is 2. See that? I did it mentally, you know, in my head, but that's basically what it is. Pretty easy. So it's going to be 10 times 2. So that will be 20 decibel. Did I say 100? 100? Anyway, it's 20, right? So, got it, guys? Okay. Here's another one from the book. I have another one in my notes, but I'll let me go to the book again. Okay, that's example 12.8. Let's do that. Page 76, right there. He says a 10-minute exposure to 120 decibel sound, which is the, remember, the 120 is what is the threshold of pain. It's going to be painful on your ear to hear that sound. You see what I'm saying? So 120 decibel sound typically shifts your threshold of hearing temporarily from 0 to 28. In other words, you become hard of hearing temporarily. Okay, if you're exposed to that, let's say, I have experienced that myself. You know, attending rock concert back in the 80s when I was around your age. You become almost deaf as you get out of the concert after hearing, you know, heavy metal. You come out, and then for the next few hours, you just don't hear very, very well. You're kind of hard, you know, you become hard of hearing. It's because your level of hearing shifts up to a certain level. So anyway, he says here, a 10-minute exposure to 120 decibel of sound shifts your threshold of hearing temporarily from 0 to 28 decibel. Studies have shown that the average 10 years of exposure to 92 decibel sound causes permanent shift to 28. That permanent shift, you become basically hard of hearing. What intensities correspond to 28 and 92? So basically what we're doing here, we're doing the reverse. See, up to in this example here, we had given the intensity in watt per meter squared. Now, what if we have it in decibel? What is it in watt per meter squared? Okay, so that requires some algebra, some knowledge of algebra in logarithmic algebra. So before I do this problem, I want to show you some algebra here. Review of algebra. Now, nothing fancy, and don't be afraid of that. So let's say this is my formula, beta equals 10 log I over I naught, okay? What he's asking basically is solve for I. That's basically what he's asking for. So what I want to do it once and for all. You don't need to do it every time. So I'm gonna solve for I. You're gonna write that equation. So every time you need I, you just plug in that equation. You don't need to go through the steps again. So we're gonna do it just once and for all. I'm gonna do it for you. Here's how you do it. All right. So remember, we're gonna solve for I. So the first thing I need to do, I need to isolate the log. Okay. So I'm gonna move this 10 to the other side. So it becomes beta over 10 equals to log I over I naught. Okay, so far? Now I'm going to put everything to the base 10. In other words, like that. 10 to the power of beta over 10 equals to 10 to the power of log I over I naught. I hope you remember that stuff from algebra. So what's going to happen, if you remember, 10 to the power of log x is equal to what? Is equal to x. All right, go back to your algebra book and look it up. So this becomes I over I naught, and I have gotten rid of the log, and that's 10 to the power of beta over 10. And therefore, cross multiply, I is equal to I naught times 10 to the power of beta over 10. And that's basically the formula. Again, you don't need to go through this again. You can just write down this formula in your notebook, and you can use this one. Got it? Okay. Put a parenthesis there, make it look prettier. Beta. Okay. All right. So now, go back to our example. Uh, 12.8. So he said, what are, okay, after all this information about threshold of hearing and threshold of pain, so we have two. We have one is beta 1 equal 28 decibels, and then beta 2 is 92 decibels. All right? Okay, so he said 10 years of exposure to 92 decibel sound causes permanent shift of up to 28 decibel. Okay, that's an interesting example, actually. I didn't know that. Anyway, so what is it? Well, let's see. So I can just use this equation right here, the one right there. So for beta 1, so I'm just going to call it I1, and that's equal to I naught, which is 10 to the negative 12, times 10 to the power of what? Beta, which is 28 divided by 10. In other words, this is 10 to the negative 12 times 10 to the power of 2.8. See that? All you need is to use your calculator. Please use it with me right now so you don't make mistakes. So I want to get first 10 to the power of 10. Excuse me, 10 to the power of 2.8. So 10 to the power of 2.8 equals, I got 630.957. So I have here 10 to the negative 12. I'll come back to this in a sec. I got 630.96. Okay, and then I multiply this by negative 12. Answer, I got 8.3. 8.3 watt per meter squared. Oh, I forgot there is something in the back. Oops, sorry. 8.3 times, I'm sorry, I read it wrong. I got 6.3 times 10 to the negative 10 watt per meter squared. Let me check what he got. Yeah, there we go. 6.3 times 10 to the negative 10 watt per meter squared. Okay, good. Then we can do the same thing for I2. Again, you don't need to calculate this formula again. It's right here, so you just plug it in again. So that's going to be 10 to the negative 12 times 10 to the power of 92 over 10. Is that right? And that will give me 10 to the negative 12 times 10 to the power of 9.2. And then when we calculate that, I'm just going to cheat the answer of the book. It is 1.6 negative 3 right there. 1.6 times 10 negative. I hope you'll be able to do that with that. Please practice with your calculator. Make sure that you get it right. 1.6 times 10 to the negative 3 watt per meter squared. That's really loud, 92. What is 92 on the table? Just out of curiosity. 92 is close to, okay, so it's close to a drill. Okay. So in other words, if you are a carpenter and you're constantly drilling holes and putting screws in there and nails, whatever, eventually that will affect your hearing because it's just so loud. Okay. One more example before I move on, and that is example, a bird sings in a meadow. Next example, same page. This one is a little toughy, so pay attention to it. He says, consider an idealized model of a sound emitted by a singing bird. There was a little birdie here. Assume that the bird acts as a point source of sound with a constant power, okay? Remember, those lines right there, those are spheres, right? So these are spherical waves, and then you have two observers. Remember, we talked about those two observers at different distances. So we got observer 1 right here, and then this guy is further away from him at P2. Okay, we call him P2. Okay, assume that the bird acts as a point source of sound with a constant power so that the intensity is given by equation blah, blah, blah. Okay, by how many decibel does the sound intensity level drop when you move to a point twice as far as the bird? Okay. All right. I did it slightly different from the book, so you may want to read how the book did it, and then I'm going to show you my method of doing it. Okay. First thing I want to do is, let me draw the picture for you. Next example, 12.9. So the picture, I'm not going to draw a bird with two guys standing there. I'm just going to draw a source. So here is the birdie right here. This is the sound source. And here is the spherical waves. So we have the first observers right here. Okay. There we go. And this is observer number 1. And then observer number 2, let's just put them, let's say put them somewhere here. Can never draw a perfect ear, can I? Try it again. Something like that. That's 2, okay? Any numbers given to us? No. Oh, okay. So he says this observer is a distance r away, but this observer is 2r away, double the distance. Is that right? Let me just go back to the problem. Sorry. He said, assume that the bird is at point. Okay. By how many decibel does the sound intensity level drop when you move to a point twice? Oh, it's not two observers, like the same person is moving. But anyway, it doesn't matter. Okay, so you move twice as far. So, okay, so you started with a distance r, and then now he is 2r away. Got it? Okay. So let's start with r. Again, let me go back to the formula that I have derived for you earlier. Let me go back to it very quickly. Right here. Remember this one? The Siren. I called it the Siren right here. Okay, and then we have derived this formula right here. So I'm going to write it down again. So basically the formula says I1 over R2 squared equals I2 over R1 squared. Is that right? Okay. So how do we do it? Well, we know that if I call this, let me call this R1, and this is R2, all right? So in this case, R1 is equal to R, and R2 is equal to 2R. So I'm going to plug in those things in there. So in this case, this formula becomes I1. I'll tell you what, let me put I1 over I2 first. I1 over I2, it becomes, if I just cross multiply, I get R2 squared over R1 squared, okay? So R2 here is 2R, and this one is R, all of them squared, correct? So basically the R's cancel out, I end up with 4. Make sense? In other words, I1 is equal to 4 times I2. What does that mean? It means the following. When the observer was located at position 1, okay, his intensity was I1, okay, just I1. When he moved double the distance, his intensity is 4I2. So here it has increased, decreased by a factor of 4. Got it? Make sense? Okay. So now this is in terms of intensity, I. Now we want it in terms of decibel, intensity level. Intensity means decibel. Okay. How do we do it in terms of decibel? How much is that decibel? Well, the best way to do it is basically we can use a similar formula like this one, but we are using the decibel formula. Here's how it works. At position R1, we had beta 1 equals to 10 log I1 over I0. And at position 2, we had beta 2 equals to 10 log I2 over I0. Now the question is, how do they compare with each other? Okay, how do we compare them? Well, one way to do that is to subtract them, because I want to see the difference between them. You see what I'm saying? But before I do that, I know that I2, remember that I2 is equal to 4I1. Is that right? You see what I'm saying? So in this case, I will have this beta 2 is equal to 10 log 4I1 over I0. Is that okay? Oops, I think I messed up my notation. I hope you're not screaming at me by now. We said that in this part, I1 is equal to 4I2. So what I wanted to do is to write it in terms of I2, not I1. Sorry, this should have been I1. Let me go back here. This is wrong here. Sorry. Okay. So I hope those two formulas are fine, right? So we have here beta 1, 10 log I1 over I0, but I1 is equal to 4I2. So I'm going to write it down. 4I2 over I0. And then here, I'm just going to leave it the way it is, okay? So there we go. So I have that. And then I want to find the difference between them, okay? So rather than making the ratio here, I'm going to make it get the difference between them. So get the difference. Delta beta, okay? So that means it is beta 2 minus beta 1. That's what I want to do. So when we do that, and I just plug it in. So I have here beta 2 is 10 log I2 over I naught minus 10 log 4I2 over I naught, okay? And then you know how logs combine together, correct? So take 10 as a common factor, and that will give me log, you know, when logs combine, if you have log V minus log W, let's say, that's equal to log V over W. Remember that? I promise we're not going to be doing a lot of algebra during the test at all, okay? So don't expect that you're going to be doing algebra like that during any of the exams, okay? So don't panic. You may see it on the homework, but you're not going to see it on the exam, okay? So anyway, so we have log, and then we just basically divide the two arguments together. So that's going to be I2 over I naught times, if you do the algebra, I naught over 4I2, and then the I2's cancel out, and the I naught cancel out, and I end up with 10 log 1 over 4. See that? Now I can use my calculator immediately and get an answer to that, but let me play with it just a little bit. So this 1 over 4 is what? Is log to the power of 4 to the negative 1. And that's equal to 10 log 2 to the negative 2. So that gives me negative 10 times 2 log 2. And log 2, if you look it up, use my calculator for that, log 2. And then you work it out. Log 2 is basically 0.3. And this one is negative 20. And that gives me negative 6.02 decibel. So delta beta is that. Now, what's the meaning of that minus sign? It's the meaning of it is decrease, okay? So that's a decrease in decibel level, dP, to 6.02 decibels in sound intensity. Okay? Okay, one more example on sound intensity. Again, this is my own. The time now is almost 1:30. I don't know if I told you before, I cannot exceed 2 hours, otherwise the system will not allow me to upload the video. That's just the nature of the program that I'm using. And I still have one more topic, which is the Doppler effect to cover. It's not a difficult topic at all. Anyway, here's an example. Basically, it says, let me write it down for you. You have a very interesting example. It says you have a noisy machine in a factory produces 80 decibel. Okay, you can imagine this is kind of a very loud machine, 80 decibel, okay? It is a loud machine. So the question is, how many identical machines could you add to the factory without exceeding 90 decibel. Remember, these are kind of a state federal laws that certain you know, the factories or whatever place that cannot exceed a certain level of decibel. So 90 decibel limit. So let's say this factory has a limit that all the noise, all the sound level in that factory cannot exceed 90. So, all right, I have a machine that is producing 80 decibel. Now, if I put another machine that is also producing 80 decibel, what would be the total decibel from those two? It's not going to be 160, guys, okay? Sound level don't add up like that, okay? So it would be, let's say if you add it up, it's not going to be, you know, 160, or they add up logarithmically. So this is what we're going to be doing, okay? That's why this example I find very interesting. So make sure you understand what the example is. So I have a machine in the factory. I need to add several others, but I am limited by the rules and regulation of the factory that sound level cannot exceed 90 decibel. It's just too much on the workers, okay? So how many machines I can add? That's the question. So how do we do it? Well, here's how it works. First thing, you need to think about it in terms of intensity. So we know that the decibel level beta is equal to 10 log I over I naught. Okay? Here is the interesting part. If I have a machine that produces a certain sound in intensity I, some number watt per meter squared, okay? If I bring in another machine, identical machine, okay, the total intensity is actually doubled. So in other words, if this is I1, sorry, let's just make it I. If I add another machine, it's going to be 2I. A 3 machine is going to be 3I, and so on. So in other words, intensity I, watt per meter squared, add up, you know, 1, 2, 3. You can add them up together. 1 plus 1 equals 2. You'll get that. Okay? But in terms of decibel, they cannot add up because these are logarithmic scale. You see what I'm saying? So in other words, how many machines? Well, the number of machines is going to be, let's call it a number, n. So in other words, for a decibel level of 90 decibels, I have 10 log ni over I naught, where I'm going to solve for n, the number of machines. You understand that? So n here is the number of machines that I can add. Okay? So all I need to do now is to solve for n. But before I do that, I need to know the corresponding I. For what? For 80. You see what I'm saying? So before I do that, I need to go back, use the same formula, and ask the question, what is the corresponding 80? If I have 80 decibel, what is the corresponding I? Well, I can use this formula and do the algebra, or I can just go back to that formula that I gave you. What is it? There, it's right here. This equation right here. Okay, so I'm going to use this formula, plug in beta here for 80, and see what is the corresponding intensity in watt per meter squared. You got it? So I'm going to use this formula right there. So I have here I equals I naught times 10 to the power of beta over 10, correct? So I'll just plug it in. So I have here 10 to the negative 12 times 10, 80 over 10. So that gives me 10 to the negative 12 times 10 to the power of 8. So that gives me the intensity here is 10 to the power of negative 4. Is that right? Watt per meter squared. There we go. Now I know what the intensity is. So I take that and plug it back in there. So now I come back here. So I have 90 equals to 10 log n times 10 to the negative 4 over 10 to the negative 12. I hope you're following me on that. And then just clean it up. Move this 10 right here to the other side. It becomes a 9. And that's log n times 10 to the power of 12 negative 4, and that'll be 8. Is that right, guys? And then all I need to do now is to convert it to a exponential form. So that becomes 10 to the power of 9 equals n times 10 to the 8, excuse me. And then you just solve for n. So n here will be 10 to the 9 times 10 to the negative 8. So n here is 10 machines. So I can add up to 10 machines and it will not exceed 90 decibels. Got it? Okay, good. Okay, the last topic that I want to talk about is Doppler effect. There are other topics in the chapter. You can simply ignore them. And we will, basically what's covered in the chapter is what I'm covering here in the video. All right? So the Doppler effect, this is the last one, just a big chapter. The Doppler effect. Okay? Doppler effect, you will notice it. Actually, you notice it all the time. You just don't think about it. It happens whenever there is a relative motion between a source and an observer. Okay, so it happens when you have a relative motion between a source and observer. Let me explain to you. Imagine you're standing on the at the pavement of a street. Let's say on the shoulder of a street, right on the side of the street, and there are no cars except one car coming from a faraway distance. You can see the car coming. Okay. So you will hear, the way you hear the car coming towards you, and the car as it passes you and recedes away from you, it will be different. You'll hear the car coming towards you like this. And then as it recedes away from you, the sound of the car kind of gets, the pitch of the sound gets lower. Okay? I'm sure you've heard that before. You observe it, but you probably didn't think about it. But this is called the Doppler effect. Let me explain it to you. Let's say here is the car. And the car is going in this direction. This is the street, of course. And here is you. I'm going to symbolize you with an ear. Nice looking here. And so the car is going like that, okay? And then the car passes you. So here is a car, the same car. Now it passes you. And, whoops. Disappeared. There we go. There we go. And now the car, of course, is going this direction. Okay. What's the difference between the two cars here, the two situations here? The difference is the following. As the car is coming towards you, we're talking about this car here. As the car is coming towards you, it's making a lot of sound. Basically, the tires are pounding the street, so it's making a lot of sound. And of course, the engine is roaring. So this car, and of course, you have the air drag. The air is hitting the car. All this combination of acoustics, all these wave sound, produces the sound of the coming car towards you, okay? So this sound that is coming from the car is, of course, going at the speed of sound towards your ear like that. See that? So this is the speed of the car V right here. This is the speed of the car V. And then this is the speed of sound coming towards you right there. This is the V, velocity of sound. Okay? However, as the car moves away from you, receding from you, look at the direction of the velocity of the car, say going 50 miles an hour, going this way, but the sound is going this way towards your ear. See that? In other words, here in the first situation, the speed that you're going to hear, the speed of sound that will actually coming towards your ear, is the speed of sound being carried on the car, so that the speed really is the speed of sound plus the speed of the car. Where in this situation, you have the speed of sound minus the speed of the car. You see that? And that's why you hear a higher pitch as the car comes towards you. And this one is a lower pitch. Okay? So, like we said, the Doppler effect happens whenever there exists a relative motion between the source and observer, just like the situation that I've just showed you here. Okay, and there are three situations, or three conditions, or three scenarios that could happen. We're going to go over those very quickly. So there are three scenarios. Your book doesn't do a good job explaining them, so I'm going to give you a bunch of formulas. Please write them down as we go along. So there are three scenarios. The first scenario is that, before I do the scenario, I want to give you some symbolism. So when I say S here, I mean source, the source of sound, that is. Okay. O means observer. You know, the ear thing. Okay. And then you have V is the speed of sound. Not V sub S, okay? Just V, which is a number, 345. And then you have V sub S is the speed of the observer, of the source. And V sub O, this not, V sub O is the speed of observer. Okay, these are the notations that we're going to be using. Okay, they're slightly different from the book, but those are the ones that I'm used to. So here is the following scenario, the three scenarios. Scenario number one is that the source is at rest and the observer is in motion. Okay? What does that mean? Well, let's say, for example, what does that mean? You have the source of sound is at rest. Let's say that you're driving your car downtown, and then there is a band playing, outside. There's a band playing on the street, and you pass by it. Okay, you're not producing any sound. You are hearing the sound, but here, the sound source is at rest. It's just right there on the street, but you're the observer is in motion. Okay, so as you come towards the source, and then as you move away from it, you will notice that Doppler effect. And then the frequency that you're going to measure, we're going to call it F prime. This is observed frequency. Maybe I should have written that. Observed frequency. So we have one more. That's observed frequency. Frequency. Okay? And that's F here, frequency of sound. Frequency of the source, that is, sorry. Honestly, this stuff is really easy, okay? It sounds like I'm making it hard, but it's really easy. When we start doing problems, I'll show you examples. Okay, so if you have, like I said, okay, this is the first scenario. Scenario number one is that I have the source at rest, observer is in motion. Then the observed frequency F prime is equal to F V over V plus or minus V naught over V. Okay, what does that mean? It means the following. You pick, well, which one do I pick, plus or minus? Well, it depends on the problem. You pick plus if it's moving, if you're moving toward the source. You pick minus if you're moving away. Okay? I'm just going to write down the formulas now, and then we'll do examples, okay? Just bear with me. Second scenario. Here I have the source is in motion, and the observer is at rest. What does that mean? Again, you are on the street and you see a siren, an ambulance coming. So you see it coming towards you and then away from you, okay? And then you want to measure the observed frequency, okay? In this case, the observed frequency F prime is equal to F times V over V minus plus VS, There we go. Okay. Just like that. Okay. Where in this case minus here indicates the siren or the ambulance or the source is moving toward or approaching towards or approaching. Okay. If it's plus, it's moving away from O. Okay. And then the last one, then we'll do some examples and show you how easy it is that the source is in motion and the observer is also in motion. Well, what does that mean? Well, again, you're driving a car and you see an ambulance or a fire truck behind you. I'm sure we all have seen that. So you see, so you are moving and the fire truck is moving and the fire truck producing a sound. Now, is the fire truck moving towards you or away from you? You know, again, we have a different scenario. So here we have the observed frequency, f prime, is going to be the frequency of the fire truck, if you will. And that's equal to V, notice the plus and minus, plus minus VO over V, watch this, minus plus VS. Okay, write it exactly as you see it, guys. Okay, where the upper signs, in other words, you get to pick plus and a minus, the upper. It means the source is toward each, or actually the source and the observer are toward each other. So towards each other. In other words, I am driving my car, you know, I'm going north and I see the fire truck going south in the opposite direction towards me, okay? On the other lane, of course, okay? So this, we are going towards each other, and then you're gonna hear, of course, a higher pitch because it's moving towards you. So anyway, so we're moving towards each other, the source and the observer. And then you take the lower signs, which is what, minus and a plus, and that would be if they are moving away, okay? And that's basically the end of it, okay? So please write them down on a sheet of paper. I'm not going to come back to them, and we're just going to do how many examples do I have here? 1, 2 examples. I think this should be good enough, and then we'll finish the lecture. Okay, here's an example. It says a train moving with a speed 40 meters per second sounds its whistle with a frequency equals to 500 hertz. Okay? And there are part A and part B. Part A, he said, determine the frequency heard by a stationary observer as the train approaches the observer. Okay? So what do we have here, guys? Here we have the source is in motion, the train, and the observer at rest, right? So we go back to the sheet that of formulas, and we pick which one is that. Well, let me go back. So source in motion and observer at rest, which is right here. So we're going to use this one, And he said as it approaches you, so it's going to be approaching, so we're going to pick the minus sign. You get that? So basically this is the formula. So we're just going to go f prime equals f v minus vs, and then s here for the speed of the source. So that he said the frequency of the whistle is 500. In other words, this is how the whistle is designed. It was manufactured to produce 500 hertz. So that's going to be 500 here times v by itself is the speed of sound, 345 divided by 345 minus the speed of sound, the source is 40. Very quickly, let me see. You know, each book has a different speed of sound, and for the speed of sound, okay, so in your book it's 340. So make sure I'm using my example, and each book has their own thing. So if our book uses 340, so let me put it in writing, textbook speed of sound is equal to 340. Please use that. Don't use 345 like I'm doing here. Unfortunately, I'm running out of time, so I don't have the time to change it to 340. But anyway, use this one when you do homework. Otherwise, you're not going to get it right. So anyway, when we do it this way, guys, so let me go back to the formula that I started here. And when we calculate that, you're going to get a higher pitch because it's moving towards. So that's going to be 566 hertz. Part B, he says, as the train recedes from O. Well, in this case, what do? We use the same formula, except that we have the plus sign. So it will be V over V plus Vs. And then we just plug it in. So it's going to be 500, 345, again, use 340, over 345 plus 40. And then you're going to get a lower pitch, and that will be 488 hertz. Okay. The next example, you have it's called a noisy siren. We have an ambulance. Travels down the road with a speed of 75 miles an hour. The siren emits a sound of frequency f equals to 400 hertz. What frequency heard by a passenger in the car traveling? So we have a passenger here in a car traveling 55 miles an hour in the opposite direction. Okay, and there are two parts, A and B. The car approaches the ambulance, and the other one is car move away. Okay, I'm sure you know how to do it. Let me just give you a quick sketch of how to do that. First thing you need to do, you want to convert the speeds to meter per second. So the speed of the observer is 55 miles per hour, and that makes it 24.6 meter per second. And then the speed of the source is 75 miles per hour, and that makes it 33.5 meters per second. And then A, for part A, the car approach. Approaches. So in this case, we're going to go back to that table, and we're going to use this one because they both are in motion. So we're going to use this one, and because it's approach, which means toward each other, so we're going to use the upper, plus and minus. You got that, guys? So we're going to do that. So the formula will become F prime is equal to F, and then V plus VO over V minus VS, excuse me. If I can erase that thing, there we go. And then you just plug it in. So we have here F prime is going to be equal to 400, the frequency given to us, right? It's right here. And then 345, again, in our book we use 340 plus 24.6 divided by 345 minus 33.5, and then you just work it out and you'll get 475 hertz. Okay, and then the next part, he says away, is moving away. So what do? You basically, the frequency is equal to F V minus V naught over V plus Vs. And then you just plug it in. And then we have here 400, 345 minus 24.6 divided by 345 plus 33.5, and then we calculate that, and we end up with F prime is equal to 339 hertz. And there we go. Okay? I think I'm going to stop here. I'm running out of time, and I think I'm pretty much done with what we covered, what we needed to cover. So please let me know if you have any questions. Bye-bye.